so that at least nobody will miss anything after this point. Again, you see how that worked when somebody just started talking. I think, I don't think that many people are going to speak up. So feel free to, unmute yourself and, ask a question anytime you have one. Okay. So this. So most of you, why is this doing this? Let's see. So I presume most of you have already logged in on Blackboard. I think a large number of you also have gone to the Piazza forum for the course. If you have any, if any of you is not able to access Piazza, let me know. And again, you can send me email if you're not able to access Piazza. But once you can access Piazza, then you can, oh my God. Where are you? Somebody is waiting. Okay. So I hope. Okay, so all right. So I wouldn't know what to do. So hopefully we'll resolve these. There's one student who's not able to access, so we'll hopefully resolve that soon. Yeah, I think everybody who wanted to get into the course is in. So let's talk about the course content, right? So, we are going to talk about logical and mathematical foundations of, computer science. So the course is basically organized into sort of 4 units. The first unit is about logic and proofs. So we will learn about propositional logic, truth tables, implications, things like that, and predicate and quantifiers. Again, some of these terms may or may not make sense to you, which is perfectly all right, because if you already knew every term, then you would be wasting your time here, right? So we'll be learning about sets, infinite sets, relations, functions, and recursion and functional programming, which is where that little bit of programming might come up, okay? Then we will spend a little bit of time on structures like trees, graphs, partial orders, and so on. That is your second unit. The third unit is about counting, which involves, how do you, you know, how many ways are there to do something, and that feeds into how you calculate the runtime of various algorithms. It also feeds into probabilities, which and the probability is really core to a lot of computer science we do, including algorithms, artificial intelligence, and data analysis, and so on. So we'll be covering all of these 4 units, but more importantly, the goal is to sort of, again, let me emphasize again, we'll be talking about bringing up fun problems and trying to figure out how to solve these problems. Sometimes the problems may not have, seem to have a structure, and then the goal is to find the structure which makes the problem easy to solve. So so the textbook, right? So it is an online textbook, and there will be some lecture notes and the slides. My plan at this point is to, primarily, write on my iPad, very similar to how I would be writing on the whiteboard if we were meeting in person, right? So that's what I'm going to try to do. Let's see how the technology, how well the technology cooperates, and then we'll see whether we need to try something else. So this is the textbook. The textbook is online, and you don't need to buy anything. It's a really, really wonderful textbook. A lot of interesting problems, puzzles, and it's something that you can read in your leisure time. It's not really like a textbook. Then there is also this course material from MIT, which includes a lot of lecture slides and videos and so on. All of that is all quite useful, and if you have time, by all means, you should go look at that. But realistically, you may not have a lot of time to look at the video lectures. But if you're interested, definitely look at the problems, right? So the problems are interesting. Some of the slides may be interesting, and take a look at them, because you will learn. Obviously, you can learn more by looking those up, because what we will cover here is going to have some commonality with what they teach, but there will also be a lot of differences, and therefore, if you look at that material, you will know about some new topics that we don't get to cover in this in the class here. So grading will be based mostly on exams and some homeworks, and I'm trying to figure out exactly how the exams are going to be done. Last semester, we used a piece of software called Lockdown Browser to conduct exams remotely. There may be some alternatives this semester, and I'll once I figure it out, I will let you know. The backup option is the Lockdown Browser, which basically what it means is that people should have either a Windows PC or an iPad, right? So that's the compatibility, hardware compatibility for hardware and software compatibility for this lockdown browser. It's a special type of browser which, as the name suggests, it locks down the interface so that people are not able to, do other things while they're taking the exam, such as, surfing on the internet. It captures, a video of during the exam, so we can look at exactly what you're doing during the exam. So it's essentially a way of doing remote proctoring, remote, offline proctoring, because it's recorded and then we look at it. It's not the best arrangement, but it is definitely, much better than no proctoring, which is really not a good way to, conduct an exam. So the exact, split between exams and homeworks will, can vary a little bit. So maybe it can go from 70 to 80% for exams and, 20 to 30% for homework. So that's the range of variation you can expect. And some of this will also depend upon whether, again, whether we get to do, whether we do this lockdown browser or we have better arrangement for exams. So so can you do me a favor, and can those of you who are on campus, can you lift your hand? There is a way to lift your hand in Zoom. Can you try that? Does anybody have their hands raised? Because I don't see any indication here. Let's try this.
You have to click on participants, and you'll see the blue hand next to whoever has their hand raised.
Yeah, but I thought it usually also summarizes how many people have hands up.
What I'm seeing is like 20-ish, maybe 10, 15.
Yeah, it may bring them up. Okay, I see that there are about, maybe 10 or 12 people. So I guess most of the class is remote. Okay, so so there will be, again, this is mostly a mathematical course, which means that you will, okay, so good. People who had difficulty, at least one of them who had difficulty has joined, so. Okay, so, so this is a mathematical course, which means that most of the homeworks will be in the form of problem sets, and you will work out the problem sets and submit them, okay? So you can work on these problem sets in groups, right? And we don't really say how large the group can be. You can decide what group size works, well for you. Yeah, you can put your hands down. Thank you. I should have said that. Okay, so yeah, how large a group you can decide, because the goal of working in groups is so that you learn more, right? Because sometimes if you just work on your own, then you can get stuck and not make any progress and not learn anything. And so instead, if you work in a group, then when one person gets stuck, some other person can have an idea, and then you can make progress. And more importantly, you can learn from each other, because each person may have a different approach for solving the problem. And that way everybody learns. So this group assignments work well. But again, you need to decide who's your group, and what size group works for you. And then when you write up the problem and you submit it, we want you to do that individually, okay? So even though you work in groups, you should submit individually. And whenever you submit individually, if someone else solves a problem and you didn't really have an idea, and you just understood the problem from the solution, you should say that, right? Because there is no, you get credit for what is written on the on your submission. Not so whether you found the solution yourself or somebody else found the solution, it doesn't matter for how much credit you get, right? But it does matter, because if you get the solution from someone and you don't acknowledge that, then that is a form of academic dishonesty, and we really don't want to see that, okay? So one of the things that we want to teach you in this course is, academic honesty, right? So how to, what is ethical, what is not ethical, and what you can do, and how you can collaborate, how you cannot collaborate, what you should acknowledge about others' work, and so on, right? So you need to really, do that right. And to help you with that, your very first homework assignment is going to be about, on this topic, right? So the topic of plagiarism and academic honesty. So we will give you, I'll distribute a 2-page or so description of, what we expect from you, what kind of behavior is okay, what is not acceptable, and so on. And you need to read that, and then you need to hand copy those 2 pages and then submit it. Okay, so that's your very first homework. So hopefully if you hand copy it, then you will have to read it carefully and understand what is being said. Okay. So are there any questions on what I've said so far? Any questions about how the course is going to be run? Again, we have 2 lectures and a recitation. Between the lecture and recitation, we'll take like a 20-minute break, okay? So that you can a little bit unwind a bit, and then come back. And sometimes, we will maintain continuity and just the lecture and recitation. There may not be a difference. Other days, we will set aside the recitation to go over, problems of the kind that you may see in your problem sets. So as yes, you probably saw in one of these slides, I expect to have 6 to 9 homeworks. Okay, my goal is to give you more homeworks that are somewhat smaller in size, rather than give you like 5 large homeworks, because that makes, I think, makes it more difficult to manage your time if there are big pieces of work that suddenly land up on your desk. So we are going to try to space it out a little bit and do it more evenly throughout the semester. Anything else?
For the lockdown browser, did you say it was only compatible on Windows?
On Windows and iPad.
So does Mac OS work?
I don't believe it does. Okay, I will again, I'm hoping to avoid it, but if we will know in a couple of weeks whether that's going to work or not. Okay, and if we use it again, we'll use it for the midterm and the final. Okay, so it's not something that's going to be hanging over your head all the time. And if you use it, there will be sample exams that carry no weight, right? So you are like 1 point or 2 points, something that gives you practice so that you don't have to go into this exam with unproven, unknown, unstable technology, right? So it is definitely less stable. Somebody says it's Mac is compatible. It's probably I may just be wrong, right? So I use Linux. So the fact that it's not compatible with Linux, I might remember it as it's only compatible with Windows. So the Linux support is certainly not there. Okay, so that's unfortunate. Yeah. I don't think it works on Wine. I think it doesn't. It is not supposed to work if you install a virtual machine on top of a Linux operating system underneath. So it's supposed to work only when you run bare operating system on top of hardware, right? This is all for security, okay? But of course, if you're smart enough, right? The problem that they are trying to solve is a fundamentally unsolvable problem. And so if you are smart enough, then you can find a way to get around it. But then, it's a lot easier to cheat on many other things than the exact, right? We are counting on you not to cheat because ultimately, of course, you're cheating yourself, right? So we will do everything in our power to, prevent cheating and catch people who, abuse the trust we place in them. But ultimately, if somebody's really motivated and does not care about the repercussions, which, as you see very clearly, is an F grade, right? Then, there's really, if you're willing to take your chance, well, then you might get away with it, right? So we are going to do everything we can to make it impossible, but ultimately, we have limited power in that regard. Okay, so let's stop here and then start on the lecture material proper, okay? If there's any questions on the organization, please go ahead. Again, I would like more questions from the class because, see, the biggest, it's really challenging to teach on Zoom. And that's because the feedback I have in terms of looking at faces, looking at body language, looking at, it's just not there. And the only form of feedback that's available is through the questions. You may think the question is, not well formed, or it may sound stupid or things like that. But every question is invaluable for the instructor because it really tells them, where the students are. And it tells me, okay, if whether I'm teaching it the right way or should I explain it in a different way. It's really invaluable. So please speak up. And that's also the only way to keep the class interesting and engaging and so on. Okay, so let's do that. So because I gave you a long lecture like this, so you're going to ask some questions now. Well, not clearly. Okay, good. So let's we're going to talk about proofs, and we will start by so what is a proof? What is the purpose of a proof? Anybody wants to tell me?
It's to show that something is true.
Okay. To be really sure that something is true. Any other reason?
It would be like to show that the equation is supported by math.
Right, but most of us, when we look at a proof, right? When somebody tells us something, we more often than not trust the statement, but we may still look at the proof. And why do we do that? Maybe maybe you don't do that yet, but you can imagine what would be another reason why proofs are useful.
Is it to? You can go first.
Whoever is speaking, the volume is too low. So if you move closer to the speaker, or yeah, go ahead.
Can you hear me now?
Better.
Okay. Is it to better understand the fundamentals and how and why that equation does what it does and proves what it proves?
Right. So it is the why, right? So we want to understand why something is true, because the why is often the most interesting part, right? The what is sometimes interesting, but the why is often much more interesting. And it really tells us the reason why something is true. And that's why, so we should use, so the primary purpose of the proofs that we will look at here is not so much to establish something is true, because obviously, we already know, somebody has already proved, right? Or somebody has disproved this statement. So the only reason why we are studying it is because, we are trying to understand why something is true. So let's start with the Pythagorean theorem, which most of you have seen for a long time, right? So you have a right-angled triangle, and the hypotenuse has length C, and the two other sides have lengths A and B. And for the purpose of this, we are going to say this A is less than B is less than C, okay? This kind of helps in the proof. So, so the theorem says A squared plus B squared equals C squared, right? So have people, have any one of you seen the proof of this theorem? If so, speak up and tell me how it is proved.
I've seen one like geometric way of proving it by having a square with like another square inscribed within it, where the larger square has sides A plus B, and you find the area of the smaller one by subtracting the triangles from the bigger one.
Right. So that is this picture, my attempt to draw that on a piece of paper, right? So so what we have done is we have taken this triangle, right? And we have arranged it with this particular vertex towards the middle of a square, right? So all the four sides are the correspond hypotenuses, right? So we have 4 times this rectangle, right? And now you can calculate, what is So you see that there are 4 instances of the triangle which we have taken and we have kind of rotated it and arranged them into a square, right? So this arrangement, does anybody have any questions about how we have arranged this, right? So we have 4 of these rectangles, triangles, right? Okay, so now let's try to look at this, square in the middle. And first of all, let's convince ourselves that it is a square, right? Or even more importantly, let's convince ourselves that the triangles will line up this way, right? Because you can see that if this angle is theta, then this angle is going to be 90 minus theta, right? That's the, because again, this is the right angle. So because a triangle, the angles add up to 180 degrees, therefore these 2 angles should be complementary, right? Which means that this is theta, then this must be 90 minus theta, right? And this angle, right, is the same as that angle because it's just the same, rectangle that we have just flipped around. So which means that this is 90 minus theta. Therefore, when you put these 2 angles together, then you will correctly match that 90 degrees corner of the square, right? So clearly all of these are going to, line up against each other the way that we have drawn the picture. So one thing about these kind of pictorial proofs is that it's very easy to go wrong by, because you're just drawing and you're not quite sure that everything is precise. So this is why you always have to, check whether, things line up and whether the lengths and so on are, what you claim it to be. So, okay, so first of all, we can see that this is C on all sides and that this is going to be a square of size C on each side. And the triangles, the 4 triangles are going to, touch each other in the way it's shown. Okay, so now we just need to look at, this center part, right? And then see whether that is actually a square or not, right? And we can see that, from, again, we said the smallest side is A, the next side is B, and the largest side is C. Okay, so because of that, this whole thing that I marked as B, right? And then, so this is A, and that is B, right? So therefore, this must be B minus A, right? And you can do the same reasoning looking at, this length being B, right? And that length being A, and therefore you will get that this length is B minus A, okay? So that shows that this opening in the middle is a square of size B minus A, okay? So we haven't really done much in terms of the proof yet. We just have arranged this triangle in some way and shown that if you arrange them this way, then you'll have a B minus A square in the middle, okay? So now the proof, the way, but we certainly know that this square has an area of C square, right? So that much we know, right? So we have created a C square, and that square, C square has 4 times right? So we have 4 of these triangles. Each triangle has the area of 1/2 times base times height, which is 1/2 AB, right? And there are 4 such triangles. So we have 4 times half AB. And then we have this little b minus a square in the middle, and the area of that is equal to b minus a whole square, right? So if we just do the arithmetic here or algebra here, then you have c square equals right? So 4 times half AB is 2AB. So we have c square equals 2AB plus b minus a whole square. Now we can do the simplification. We can do b minus a whole square, right? So let's write 2AB plus, let's expand b minus a whole square, which is b square plus a square minus 2AB, right? You remember that, right? So the formula for expansion for b minus a whole square, right? So that is this. If you don't remember, of course, you can go here and then say, okay, I'm going to multiply b minus a by b minus a, and I'm going to take that. That is equals b minus a times b minus b minus a times a. And then I take the b inside, so that is b square minus ab. That's what I get if I take the b inside, right? And then if I take this in, the a in here, then you see ba minus a square, right? So then you simplify, then this minus and this minus and this minus is going to get canceled out. And then we are going to see this simplifies to b square plus a square minus, and then you have a 1 minus ab, and this minus goes here, and so you get minus 2ab, right? So you can, sometimes if you don't remember, you can still derive things from first principles. But other times it just takes too long, and so you better remember, right? So in this case, it's okay. So we come back here, and we have expanded b minus a whole square. And then you can see that this 2ab and that 2ab are going to cancel out. So you have b square plus a square, right? So we did some, we drew a picture, we did some geometric reasoning, and then we did some algebra, and then we are able to prove that c square equals b square plus a square, right? So let's see. Is that okay? Some people are saying yes, some people are not so sure. Okay, so some of this, of course, what you need to do is you need to try to do this yourself, right? Because especially these derivations, beyond a point, it gets too difficult to follow, and so it's so you should definitely try to do this on your own. Okay, so this is one way of proving. So we arrange them into this square, and then we do some algebra, and then we have the proof. Okay, so now let's say I don't want to do algebra. I like picture proofs, and I want to stick with picture proofs. So is there another way of proving the same thing? Okay, so that's what we are going to try to do in here, right? So again, I'm trying to draw these pictures by hand, which you can see is not perfect. So what we have done here is we have taken this picture, right, with 4 triangles, and a B minus A square in the middle, right? And we are rearranging them, right? So we put two of these triangles on their, together on their hypotenuses, which means that you get a rectangle of size, A times B, right? So two of those triangles make this rectangle, two of these make that rectangle, right? And this is the B minus A square sitting in here, right? So you can see that the two so we have put two triangles into one rectangle and another two triangles into one rectangle, and then we slide this B minus A square, right, over here, right? Now, let's look at the area of this whole thing, right? So now you can see that this length is B minus A. And you can also see that this length is A, right? Because this is the smallest side of the triangle. So this side is A, this is B minus A. Therefore, this whole thing is going to be size B, right? And the same way, you can look over here and you can show that this whole thing is B, okay? So the area of that square, right, is obviously B square because it's a square with size B on each side. Similarly, you can see that here is an A by A square. So that is A square, and then we have so notice that, so we have this picture, right, consists of this square, right, which is a B by B square, and then this square, which is an A by A square, right? So therefore, the total area of this arrangement, this whole arrangement, is just B square plus A square. But we got to this arrangement by simply taking the pieces from here and rearranging them, right? So therefore, the area over here, right, this area should be the same as this area because all we did was to rearrange the tiles, right? So we took the same tiles, we rearranged them. So the area has to be the same. And we have calculated what is the area here, and that comes to be B square plus A square. And we calculated the area here, which is a square of size C, so it is C square, right? So again, because we just retiled, must be the case that this, must.
Can you explain how you got the B and the A on the right?
Okay, I will do this again. Okay, you are right. It can be confusing. Just hold on for a second.
Right.
Let me finish writing this. Okay, so let me see if I can draw this again. One of the problems is that when I draw this again, I'm going to get it wrong. So bear with me and see if I can do this again, right? So so again, what we are going to do is we are going to take so two of these triangles, right? So you have A, B, C triangle, two of these, and arrange them into a rectangle, right? So let's do that. So we get right. So this is A, B, A, B, and C. This makes sense, right? So we take the other two triangles and, you know, and I'm going to do the same thing. Once again, see? Okay, so this is again B, A, and C. Okay, so now we are going to put the B minus A piece. Okay, so okay, so we have taken this picture and taken two triangles, put them into a rectangle, taken the other two triangles, made them into a rectangle, and then we made the two rectangles into an L shape, right? And then in the middle of that L shape, we stuck this B minus A square, right? So this is the rearrangement we have done, right? That's, hopefully that's clear, right? Now? Okay, so and now what we are saying is, let us look at, let's maybe I'll use a different color and then they'll. Okay, so now what we're going to do is we are going to right, so we are going to take that square, right, the red square, okay, and then we're going to take the blue square, right? Now, you can see that so you can see that for figuring out the area of the blue square, you can see that this is A, right? So this side has length A, and you can see that you know, this side, right? So you can see that this is B, right? Because this is the side of the triangle, right? So this is B. And you can see that, so you can see that this is B minus A, right? So therefore, this has to be A, right? Because if you add this and this, you should get this whole thing, right? So this whole thing is nothing but the sum of this and that, right? So this one is B minus A and this is A. So if you add it, you get B, right? So therefore, it must be the case that this size is A. So what we have here is, what we have in purple is a square of size A, right? And so it has a size A square. And it's easier to see that this red thing has, you know, B on, it's a square of size B on each side. So this one has, Why is it not writing? So the red one has size b square. So the total area of this picture the total area of this picture is b square plus a square, right? And again, that must be the same as the area of this square, which is c square, because all we did was we took the tiles out and we rearranged them, right? So that is an area preserving transformation, right? So, so therefore, it should be the case, a square plus b square equal to c square. Okay.
So Professor, you essentially still have to start with that first, the first square constructed before you would need that one before this one. Yeah, you would need this one before the other one.
Right, because this is the yeah, this arrangement is the one that lets you prove anything, right? Once you have this arrangement, then you can either prove using algebra that you know, you can either use algebra to prove Pythagorean theorem, or you can use you know, just the clever rearrangement of tiles to arrive at the same result. Okay, so generally algebra is a much faster way of doing things than, you know, fiddling around with pictures. But sometimes you know, it's interesting to get these results by you know, doing something with the pictures.
Well, the issue was this. I mean, just looking at this, it's not obvious that the area would be c squared on this.
No. So what we are doing is that from this picture, we are saying the area is c squared, right? Because it has the triangles are arranged with the hypotenuses on the outside, right? And so this is a square with c, with the side of c. So that's why it has an area of c squared. And then what we are saying is that, well, I can take this c square and rearrange the tiles. And after I rearrange it, I can show that the rearranged thing has an area of a square plus b square. And since the rearrangement preserves the area, it must be the case that the area calculated for this picture, which is c square, must be equal to the area calculated for this picture, which is a square plus b square, right? And that's how we end up with the result, a square plus b square equals c square. Okay. So let's take another example, okay? And this one is the summation of I, right? So this is nothing but, you know, 1 plus 2 plus 3 plus 4. So can someone tell me what is the value of, what is the summation here? What is the formula for this?
N squared plus n all over 2.
Right. So otherwise we can write it as n times n plus 1 by 2. So this one is much easier to prove, and there are, you know, many ways to prove it, right? So so have you, I think more of you would have seen the proof of this, right? So how would you, so can you tell me what is the, how one would go about proving this? I mean, everybody, I mean, you probably know that this is an arithmetic progression and there is a formula for arithmetic progression, and that formula will give you this answer. but that's not the same thing as a proof.
We can. No, you can go.
Induction?
Yes, induction is a technique. I want to spend today on sort of techniques that look interesting and induction is a technique which is going to work on many theorems, and if you figure out how to use it, then you can it's a systematic technique. Systematic techniques are good because that they allow us to solve a whole range of problems without having to come up with a new way of thinking about the problem. On the other hand, a new way of thinking about the problem is more interesting than a standard way of thinking about the problem. So does anybody know of a different proof?
I think one that we saw in high school was, let's say n is equal to 5. Then you could write out the 1 plus 2 plus 3 plus 4 plus 5. But then if you write that in reverse, 5 plus 4 plus 3 plus 2 plus 1, then you add the two series together, you're practically adding 6 5 times. And so you do 6 times 5. Then if you divide that by 2, you get the answer to the series.
Okay. Okay. So I think I understand roughly what you're saying. But let's try this in a different way. I'm sure some of you have seen this, but perhaps don't, you're too modest to talk about it. So let's pair things up, right? So let's say 1 plus 2 plus 3 plus 4 plus, okay? And then on this side, let's say n right? Did I get that right? Right, 1 to n, right? So we can pair these, the first and the last element, right? So the pair will yield the sum n plus 1, right? If you add the first and the last element, then you'll get n plus 1. So now you pair the second element from both sides, right? And once again, they add up to n plus 1, right? And then the third element, again, plus 1. Fourth element, n plus 1, right? So you can see that this way, if you pair up, every pair yields the exact same sum of n plus 1, right? And how many pairs are going to be there, right? So there are going to be n by 2 pairs, right? So which means that implies that the sum will be n plus 1 times n by 2, which is the formula that we wrote before, right? So there are some details which we didn't quite go through very carefully, which is that if n is odd, then there is going to be a middle element, and the middle element will not be paired, right? So if n equal to 3, right? So you can pair 1 and 3, and you will get 4, which is n plus 1 in this case, right? But then there'll be 2 in the middle, right? So essentially, you have to pair 2 with itself. But if you work through the details, you'll see that this n by 2 will not be a whole number when you have n being odd, and it'll actually work out correctly even if the number of elements here is odd. The formula still works, but I don't want to go through that detail. You can work it out yourself. This is not very difficult, right? This is easy to see, right? So there is also a geometric way of looking at this. Right? So this time my writing is going to be even worse, but so bear with me. So I'm going to draw, like a one square to represent. So let's do this, right? One. It's going to be one square. Two. Well, this is not going to work. Let me get this. Okay, so I'm going to. That is 2, right? Then that is 3, right? And four, right? So eventually I can right? So this is n, right? So I've put one square for each, one. So 1 is represented by 1 square, 2 is represented by 2 squares, and n is represented by n squares there, right? So if I want to count all of the tiles here, right, then what I can do is I can take the area of this triangle, right? So I have a triangle here. So let me take the area of the triangle, which is going to be n times half times n, right? Because it has a height of n and a width of n, right? So the area of the triangle is going to be half times base times height, which is half n squared, right? Now, in addition, I have to count all these little triangles, half triangles that are outside, right? Outside the area of the triangle, right? So how many such half triangles are there? I mean, rather half squares are there?
N. There's n number.
Right, so there is n half squares, right? So you add that, so that is going to be half n, right? And now you do the algebra. So you do this, and then you take half n outside, then this will become n, and that will become 1, right? And so we have again n times n plus 1 by 2, right? So again, you can look at it geometrically and then come up with a proof which, sort of tells you the same thing through a different reasoning. Right? So there are many ways to prove things, and my goal is just to show you something, how some of these proofs work, to get the topic, to introduce the topic of proofs, right? So we are going to stop now, and then we'll continue, take a 20-minute break. We will reconvene at 4:50, okay? And then I have one, today we won't, there isn't really a recitation because there is really no problems to talk about because we are already talking about problems. So we'll continue, we will be more systematic about proof techniques. That's what we will do next when we reconvene. Okay. So thank you, and I'll see you in 20 minutes. Okay.
Could I ask a quick question?
Excuse me?
Sorry, could I ask a quick, slightly unrelated question?
Yeah. So whoever wants to drop out can drop out, and if somebody has a question, feel free to, I need a 10-minute break, but otherwise I'm fine.
Do you know if there's any sort of ICPC club or competitive coding club this year?
So that there is the ACM chapter, right? Last year they had these coding camps and stuff like that. But with COVID this year, I don't know exactly what is going on. But the ACM chapter is probably the best place to get more information.
All right, thank you. I'll take a look into that.
Yeah. Okay, very good. We will reconvene at 4:50.